double replacement reactions, when we're talking about solubility rules, it's all related to those double replacements, which again, it's the idea of square dancing. Right? Again, this is review. You can go back and watch videos from Unit 7 on my YouTube channel, and you can go do a refresher if you need it. Right? Remember to split your compounds up. We're looking for the second capital letter. There's one exception, and that's ammonia, which is right here. You got to look out for that. If you see more than one letter, what do you know you have? More than one capital letter, I should say, and that's a polyatomic, okay? Make sure you put parentheses around. Guys, all those little things that we did when we learned it the first time, back before Christmas in December, all those little things are for this right here, all right, to help you out, because now, what we're going to do with Net Ionic Equations today and tomorrow, in preparation for our quiz on Tuesday, which, remember guys, I sent out a reminder last night, your concentration quiz is going to be tomorrow, because I've got a practice sheet that you're going to have time at second period to work on, and then for homework, I wanted to give you guys that opportunity to really practice it all mixed together before I gave you a quiz. All right? Net Ionic Equation quiz is on Tuesday of next week, and then we have our vocab quiz on Wednesday, and test is tentatively scheduled for Thursday. If things happen, if we're out tomorrow or something like that, guys, obviously things will be pushed back a little bit as needed, so don't stress. If we're out tomorrow, the quiz tomorrow will be on Monday. Okay, it will be on Monday, so be prepared. Anyway, all those little things, guys, that I tried to teach you and get you to do early on is for this right here. So we broke this up yesterday. We had split it up. Will the subscripts automatically stay the same? No, you've got to go back and look at their charges, all right, and do the crisscross method. This is a +1, this is a -1, +1, -1. You might be really fast at this now, guys, being able to eyeball what it would be and do the crisscross method in your head. The hope is, yeah, that's kind of where you're at this point in the game. In March, it's March, by the way, did you guys realize that? Holy cow, 2 months down already for this year. All right, so this would be sodium nitrate plus ammonium hydroxide. Now, today and the rest of the year, when we write reactions, we will no longer leave them blank in terms of states of matter. They will always have to have a state of matter, and that's what we're going to start talking about learning today. All right? Table F, get your reference packets out. You need to become very familiar with this table. These are your solubility rules. We played the song yesterday. I'll probably play it again today while you're doing some work. All right? You do not have to have them memorized for this class. It's given to you. Like I said, in the future, if there's an AP class that's started the next year or two, you will have to have them memorized. That's where that song helps. But there's different tricks as well. Notice, you've got two columns. You've got ions that are soluble. These ones are insoluble. What does soluble mean? They're able to dissolve. What state of matter would soluble compounds be represented by? AQ, guys, because they're soluble, meaning they will dissolve to make a what? Solution. What's the name of our solutions? Aqueous solutions. Oh my goodness, look at that. So guys, soluble compounds, they have the state of matter that is AQ. Okay? Now, insoluble compounds, what do you think that means? They're solid, right? They can't dissolve. What do we call a solid that forms in a reaction? It's a precipitate, okay? So it's a precipitate that forms. Now also, guys, within those two kind of sets of rules and guidelines, you've got soluble ones, you've got insoluble ones. There's always exceptions to the rule. So if you have an exception to the soluble rule, what do these exceptions, what state of matter are they going to be? I'm going to do them in a different color. What do you think is going to happen with those? If they're an exception to the soluble rule. Yeah, they're going to be solid. Okay? Meaning they're going to be insoluble. And exceptions to the insoluble rules would be aqueous. Okay? So that's something you've got to keep track of. All right? And this is just going to come with practice. So if you don't master it today, if you're making those mistakes, all right, stick with it. There's going to be a lot of potential for partial credit with this stuff that we're going to do. So you got to kind of stick with it. The more you practice it, the better it's going to be. The lab that we're going to do tomorrow, you guys are actually going to go through and make different solutions and test them out and see what happens, okay, in well plates. And then you're going to write the net ionic equations that we're going to get into here today. So let's kind of talk about this. I want us to do, guys, to just kind of practice is we're going to just use our solubility rules to determine if they are soluble or insoluble. So we're going to do a couple of them together. Here's the key. All right, here's kind of the trick of the trade to make this go a little bit faster. Look at your anion. That's going to be the place you want to start. Okay, if we take a look at your solubility rules on table F, and I don't have them right here after the slide. Guys, take a look at all of these ions that are listed. Group 1, those are cations. So this is kind of a little, already we're starting off with an exception to kind of this rule that I'm trying to teach you guys. The first one's group 1 ions, they're positives. Ammonium, that's a cation as well. But if you look at all the other ones that are listed here, they are negative, meaning they are what type of ion? Anions, okay? So most of them that you have listed here for your rules are anions. Start with your anion in your compound. Where does the anion come within a compound? It's the second one. It comes last, right? Split up your compounds. Take the next 10, 15 seconds, guys. I want you to split up all these compounds with their cations and anions. So we split up our compounds, guys. Cations come first, anions come second. So when you go to figure out if they're soluble or insoluble, look at your anions first. So let's start with the first one. What's the name of this compound? Sodium acetate. So go back to your rules. Look for acetate. Where do you see acetate? Is it under the soluble or the insoluble? Yeah, right here, guys. Here's acetate. So all acetate compounds are soluble except, are there any exceptions? No, so anytime you see acetate, it's going to be soluble. So you could put an S next to that. We're just identifying if they're soluble or insoluble. Next one, K3PO4. What's the name of that compound? Which one do you guys have second? Oh, yeah, your B went different. I'm talking about F. I apologize there. My order's a little bit off. F is the one that I had. Potassium phosphate. So we're going to look at phosphate. All right, where do you see phosphate in your list? Okay, so this is saying, when you think about it, all phosphates are insoluble except when combined with group 1 ions or ammonium. So you've got to ask yourself, we know phosphate's insoluble, but what is it paired with in this example? Yeah, group 1. So that's going to make this what? Soluble. I want you guys to go through and try the rest on your own. Do the best you can. So lead, is it all lead ions that are insoluble right here? It's specifically lead 2. So you've got to look at the charge. Now, do I think they would give you on a Regents exam something other than lead 2? Probably not. But just be on the lookout for it. Okay, be on the lookout for it. Same thing with mercury. This is actually the mercury 1 ion. All right, because it's Hg2 with a 2+. We'll talk more about that later on this year. So just be on the lookout for those interesting charges like that. That's what these would look like after you use your solubility rules. All right. Go ahead and answer the next one in a little bit more practice before we get into net ionics. So when we discuss dissolution, we're thinking about dissolving solids. Okay, these reactions are the simplest, easiest reaction to write. We're going to write what's called a net ionic equation. What do you think net ionic equation means? So break it down. What's ionic refer to? What are we going to see? What's that? Charge, because we have what? Ions, right? So ions have a charge. What does that term net mean? And we've talked about it, guys, before, like net volume. All right. Is it before something's taken out? It's after something is taken out. So think about like net pay. When you guys get paychecks someday, if you have them now, you can look at your pay stub. Gross pay is what you actually earn, but then net is what you actually get because they take out taxes and insurance and all these other things. All right. So what we're looking for with net ionic equations, guys, we're showing what is active in the reaction. So in this case, solids are breaking down and they're just splitting into their individual ions. You must write the states of matter. So here we go. All we're doing is we're dissolving this in water. What we could say is, oh, we're going to put water here over our arrow or under our arrow, meaning what? What does that mean when you see something on the arrow or below the arrow? It's sort of the catalyst type piece, right? This in this case just means, hey, we're breaking it down. We're mixing it with water. Water's not going to play a part here. So we want to dissolve our solid. How do we break up our solid into the ions? Nope, that's how we get them. How do we break it up?
Just do it.
You just do it. What's the technique I showed you that you've already done today? Yeah, split them up, guys. Draw your line. Where are we drawing our line at? To see what our two ions are. Yeah, between the barium and chloride. So, now over here I've got Ba, but what is going to form when it dissolves? Is it just barium? It's got a charge, right? Because it's an ion. Guys, when those salts or when those solids break up, they form ions. They break up into ions. So here we go. If we were to draw a picture out, here's my beaker, like my solution that you guys made yesterday. I've got my barium chloride piece right here. I'm adding it here. What actually happens, though, is we've got a barium ion floating around, and then how many chlorine ions would we actually have? 2, right? How do you know 2, Maddie? Yeah, there's a subscript that tells you how many you have. So if we were to actually draw this picture out, it would look something like that. That's physically what's happening when you put it in solutions, breaking up. So we're just going to write the reaction out. So I've got my charge, Ba2+. What's the state of matter going to be on these ions, though? Aqueous, right? Because they've dissolved. So we've got to have that aqueous state of matter. Plus, how many chlorines we said we had? 2. That's my dissolution of solids reaction. All I'm doing, guys, is breaking it up. If it's soluble, I'm breaking it up. So where do we look to see if it's soluble? Table F. Solubility rules, okay? You must write the states of matter. Guys, we just wrote a net ionic equation right there. These are the simplest net ionic equations to write because we're just dissolving solids, all right? I want you guys to practice these ones. Do your best on your own. Make sure that they are, 1, soluble. If they're soluble, break them up. If they're not soluble, you can't break them up. This is what the first one would look like. Again, you got to keep track because law of conservation of matter states what, folks? Matter can't be created or destroyed in ordinary chemical reactions. So that means you have to have the same amount of substances, guys, on both sides, or pieces on every side. All right, so that's why there's a 3 Na. Oh, yeah, go ahead.
All right, 2K plus AQ plus SO4 minus AQ.
Now, is it just... Yeah, it's a 2 minus, right? Yep. Again, break it up. Show coefficients, right? Subscripts become coefficients. That's review. Most of this, guys, is review. Put parentheses around your polyatomics. It's going to make things a whole lot easier and look a lot neater. Garrett.
The second one, for the next one, K plus OH minus.
So close. What did he forget?
Oh, aqueous.
Aqueous. Gotta have, which I think you had on your paper, I'm sure. Gotta have the states of matter there. All right. Next one. Anybody? No, I'm just going to roll through it really quick. Ca2+, and that is an aqueous state of matter now because it's dissolved. 2 iodine ions, or iodide ions, I should say. And then the last one, magnesium 2+, plus 2 nitrate ions. And it's very, very critical, guys. Why is it important to, actually, let me ask you that. Why is it important to have the parentheses when you have ions? What does that tell you about the charge?
It's for the entire thing.
Yeah, it goes over the entire piece, okay? It goes over the entire piece. So, guys, we're going to take that piece that we just talked about with the dissolution of solids, and we're going to take it a step further, okay? So now it's not just dissolving solids, but it's taking 2 solutions and where we're mixing them together. And we're going to write the net ionic equation. So net means what's left over. Ionic refers to?
Charges.
Which means we have what? What are those pieces called? Which are just in general ions, okay? And then we're going to show the equation for that. Guys, if you skip steps, this is where it will get very confusing and you will get things wrong. But if you follow the process, right, like the 76ers say, trust the process, all right? If you trust the process, you're going to get to where you want to be. So our first step is we're going to write a balanced equation. It's very important that it's balanced. That's why it's in bold, it's italicized, and it's underlined. We're going to use solubility rules to determine the solubility. This is where we're going to write what's called, guys, the complete ionic equation. What does complete mean? Not a trick question. What does complete mean? The whole thing. So we're going to show all the ions, okay? But take note, you can only break apart soluble compounds. All right? Notice you got to have your charges because otherwise they're not ions. You're going to leave the insoluble compounds together. So what states of matter, guys, can we break apart? What states of matter can we break apart into ions? What? Aqueous. What states of matter do we have to leave together? Is it just solid? It's going to be also liquids and gases. Aqueous, guys, are the only ones we can break apart. They're the only ones that are defined as a solution, all right, where things break up into ions. The other ones are pure substances, can't break them apart. Step 3, we're going to cancel out spectator ions. What's a spectator? Somebody who watches. So you may think that you're part of the team when you're rooting for them, like they can hear you through your TV, or even if you actually go to a place and watch them, like go to, well, it's not Ralph Wilson Stadium anymore, but you go watch the Bills play or whoever, you're not part of the team. Your cheering has no impact on the game. I'm sorry, that's just the way it is. All right? You're a spectator. You're there watching. You're not participating in the action. All right? Would you define yourself as a spectator or a player there, Hunter, from what you said back in the fall? That's what you said. That's why I'm not. I was just making a joke there. But, guys, spectators are just watching. So we're going to cancel out what we call the spectator ions. The ones that aren't taking part in the reaction, they're staying the same throughout the whole thing. And then we're going to write the final equation. It seems like a lot. It seems very confusing. Let's just jump right in and actually practice. All right? First things first, predict your products. Okay? Part of the first step, guys, is getting your new products, balancing it. But what else do we have to have with all of our states of matter? With all of our substances, what do they all need?
We need a 2 for the AGM.
Oh, yeah, I need a 2 right here as well. Good call. But what else are we missing in our equation? States of matter. What are we going to use to figure out what states of matter we have? Table F. Go ahead and assign states of matter. So, when you go through and you've predicted your products, you've balanced the equation, you've now assigned states of matter, guys, those kind of 3 things, that's all step 1, or not step 1. Step 1 is the balanced equation. Step 2. We have now done steps 1 and 2. Okay? Step 3. Now, we're still in step 2 a little bit, actually. I spoke too soon. Part of step 2, guys, is using your solubility rules, and then we're going to write what's called the complete ionic equation. So how you will see me write this out. This first line is what I call the balanced equation, the BE. Okay? That's our balanced equation. The second line we're going to write is called the CIE, the complete ionic equation. So now we're going to split up our long balanced equation into the pieces. For this problem, what substances can I split up into ions? Can I do all of them?
All of them except AgCl.
Why do you say that, Abby?
Because it's not aqueous.
Right. All the aqueous ones are what we can split up. Okay? So if we take a look back here, guys, it says we can only break apart soluble compounds, meaning aqueous. So we're going to split those up. All right? And to do that, it's pretty simple. So I'm just going to circle. This one's going to get split up. Magnesium chloride is going to get split up. Magnesium nitrate. Silver chloride will stay the same. So here we go. Let's break them up. Split them. I'm going to use a different color. There's my line, my line, my line, my line. Okay? But I drew one too many lines because silver chloride's not going to break apart. So now let's write it out. How many silver ions do I have? 2, right? Because there's a coefficient in front. So that coefficient. Does this coefficient, guys, only count for silver? No, it also counts for nitrate. That's a review for us. So keep that in mind. What's the charge on silver? Nope. Silver is a +1. +1. All right. What's the state of matter with silver? Aqueous. So guys, all I'm doing here, I'm going to draw arrows to show you. They're just breaking apart. I've got 2 nitrates. Okay? Look what I've done. All I've done is split it. I'm showing the ions now that make up that compound that we had up above. Why are they ions? Because it's aqueous. They're soluble. In solution, they're not sticking together. They separate into their individual ions. All right? Then I'm adding my next piece. Magnesium chloride. What's the charge on magnesium? 2+. This is where having your periodic tables out are very helpful. How many chloride ions do I have? 2. Now, do I leave that as a subscript or does it become a coefficient? Coefficient, right? Remember, guys, ions. Again, this is a review from way back when we did stuff in the past. Ions will not have a subscript, okay, because they have a charge. You have one or the other, except for mercury 1. Okay, yields. Now, can I break apart silver chloride? No, so I'm dropping that down. So this broke apart into those pieces. This, though, stays the same. 2AgCl solid. Plus, and I'm going to split my last one up. Magnesium's going to come right here, 2+, and that's an aqueous state of matter, plus 2 nitrate ions. Zach had a great question. Why do we write it out all this way? Isn't this a long way of writing out what we already had? Absolutely, it's a longer way. But what this allows us to do, guys, is to now go in and see what are my spectator ions. So if we look back here, guys, remember, spectator ions, we're canceling out everything that stays the same. You've got to be able to see, do they have the same charge? Do they have the same state of matter? Is there the same number of them on both sides? So let's take a look. We're going to go ion by ion here. The first one, 2Ag1+ aqueous. Do we see the same thing on the other side of our arrow? No. So that tells us what's happened to this ion. It's not a spectator. Why? Because it's changed. If we don't see the same thing on both sides, all right, it has changed. So we're going to leave it alone. Let's look at the next piece. 2 nitrate ions, aqueous. Do we see that anywhere over here? Yeah. So what's that tell us about the nitrate? Has it changed at all? No, it's got the same charge, it's got the same state of matter, there's the same amount. It hasn't done anything in the reaction. So we're canceling out, and you guys are actually going to physically cross out your spectator ions. They have not changed. They're just there for the show. They're not taking part in the reaction. This, Zach, is why we have to write out the whole thing. Just by looking at the balanced equation, we can't necessarily tell which ions have stayed the same and which ones have changed. We have to write out and see what's actually happened. Because they could still be aqueous in different substances, but their charges might have changed, depending on what they're bonded to. And that's a change right there. Magnesium. Do I see Mg2+ aqueous on the right? Yes, I do. Right here and right here. So I'm crossing them out. The last one, do I see 2Cl- on the right? No. Okay. So we have now effectively done steps 1, 2, and 3. We've canceled out our spectator ions. So now we're going to write our final net equation. So here's the analogy, guys. The balanced equation at the top, okay, that's your gross pay. Then what we've done is we've kind of broken down that gross pay into different categories. All right? Canceling out the spectator ions. We're getting rid of stuff that we don't get to see in our final paycheck. All right? The first nitrate, that's your Social Security. The next one, there's your taxes. The next one, that's your health insurance. The next one, those are dues that you may have to pay. All right? All that stuff gets taken out of your gross paycheck to then leave you with, oh, this is what's actually in my bank account. The net ionic equation that we're about to write, that's what's left and what I would see as a direct deposit in my bank account. All right, this is how much money I'm actually getting to spend on other things. Does that make sense? All right. So we're just going to drop everything else straight down exactly as we see it. So our net ionic equation is going to be 2 silver ions aqueous state of matter, plus 2 chloride ions, aqueous state of matter, yields 2 silver chloride, 2 moles of silver chloride solid. That is the entire reaction. So we take 2 solutions. Think back when we did that in your reactions lab, where you guys took the 2 clear solutions, you mixed them together, you got a yellow precipitate. The yellow precipitate's what's left over. We would see a precipitate with this reaction. So we're interested in thinking, what actually is taking place? What's the reaction that got us to that solid? That's this right here. I know it seems like a lot. That's why we're going to practice this like crazy over the next few days. But it's very important for us to understand the mechanisms of reactions. All right? When we talk about kinetics right before spring break, we've got to understand it. Questions?
This one, right?
No, it's not homework, okay? Guys, you need space for this. So we're going to practice a couple more together. I highly recommend using a separate sheet of paper to have 3 lines for each reaction. 1 for the balanced, 1 for the complete ionic, and 1 for the net ionic. Okay? When you have water by itself as a product, guys, it's liquid. It's a mixture. You're mixing, hydrogen ions and hydroxide ions. And if you look at it, it could say that it's soluble on your table F. But you got to recognize, guys, what makes up an aqueous solution? By definition, a solution is what? Nope. A solute and a solvent. Guys, it's a mixture, meaning it's 2 separate compounds mixed together. Water mixed with water is just what? Water. So when you have water, guys, it's a liquid. That changes states of matter, right? It's not an aqueous state of matter anymore. It's a liquid. Your reactants here are also aqueous. So I'm not going to cancel that 2H plus out because it's not on the right-hand side. Nitrate is the same on both sides. Cancel is out. Barium has got the same charge and same state of matter on both sides of our arrow. Everything else, guys, changes. Right? It goes from aqueous to liquid, so it's going to drop down to be our sort of paycheck. 2H plus aqueous plus 2 OH minus, so 2 hydroxide ions, yields 2 moles of water being formed. That's what our end-all net ionic would be. Okay?